I'm sure we've all learned about exponentiation in school, right? A to the power of 3 equals a times a times a. But have you ever wondered what is repeated exponentiation? What is a to the power of a to the power of a to the power of a, and so on? My name is Ethan Yeo from Cita Christian Senior School West Campus, and my research is titled The Power of X, Visual Analysis of Exponentiation and Titration. So first of all, what is titration? Titration is repeated exponentiation. A double arrow n equals a to the power of a to the power of a, and so on for n times. So 2 double arrow 3 equals 2 to the power of 2, which is then put to the power of 2, which equals to 2 to the power of 4 equals 16. The super root of 16 to the third power is 2. We are trying to figure out the base. When we're looking for the height, we use superlogs. Superlog of 16 to the base of 2 is equal to 3. And now let us go to the research method. The problem statements for this research is number 1, investigate the properties of titration. Number 2, investigate the graphs of y equals x to the power of x. And then number 3, investigates the graphs of fx equals x double arrow n, or titration. Number 4, explore other graphs that are related to them. And then number 5, investigate any patterns in those graphs. For the methodology, for the how, I use spreadsheets on Google Sheets to calculate the values, and then also to plot them in a graph. I use graphing software like Desmos and GeoGebra. Let's take a look at the results. First of all, the graph of y equals x to the power of x. The minimum point is 1 per e, comma, e to the power of negative 1 over e. And then, let's explain why the graph looks so weird on the negative side. Well, it is a discontinuous graph, which means there are holes in it. It doesn't fully connect to each other, because the value of a negative value to the power of another negative value can either be positive or negative or even imaginary or doesn't exist. And that means that the graph goes up and down, or sometimes there's no value at all. Next, we'll take a look at the y to the power of x equals x to the power of y graph. And this actually shows a property of exponentiation, which is non-commutative. And that means that when you move around the order of the numbers, the answer or the result is not going to be the same. In this graph, you can see this orange curve. The intersection point with the line is actually e comma e. And that's very interesting. E is Euler's number. It's this very special number that's also the base of the natural logarithm. I found out that this graph is actually equivalent to y to the power of y equals x to the power of x, but it's just a little bit smaller. And the intersection point for this is actually 1 over e, comma 1 over e. And now we'll look at the function fx equals x double arrow n. The graph starts to converge into a single curve as n increases. And these boundaries is e to the power of e, and then e to the power of 1 over e. And that was proven by Euler in 1783. That is like almost 250 years ago. Now with the modern power of computers, we can see this graph. At x over e to the power of 1 over e, beyond that boundary, fx increases up to infinity. And now we'll look at the same fx, but we'll take a look at when n is a fraction. So you move it around so that the titration height is still an integer. Because this 3 over 2, you can rewrite it as a super root of power 3. We can see that all of these lines, colored in rainbow here, it will start to converge as well like before. It's at 0 until e to the power of 1 over e. So for the conclusion, the minimum y equals x to the power of x is 1 over e, comma, e to the power of negative 1 over e. And then for the y to the power of x equals x to the power of y equation, the intersection of the curve and the line is at e comma e, or Euler's number. And then for the curve in the graph of fx equals x double arrow n, it converges as n increases to infinity within the boundaries of e to the power of e, x, and then e to the power of 1 over e. And then past that, it will climb up to infinity. And lastly, I would like to leave you with a quote. If I have seen further, it is by standing on the shoulders of giants. Thank you.